Hello, I'm the magnitudal Mr. Daycock, and today I'm going to be teaching you about using de Moivre's theorem to prove trigonometric identities. Now we've already done that a little bit, but now I'm going to be looking at a slightly different example. But before we start, we need to go back to the idea of complex numbers. So a complex number can be written in modulus argument form. So if I take a complex number z, then that can be written as r multiplied by cosine theta plus I sine theta, where r is the modulus of z and theta is the argument of z. And that's really important. Now let's assume that the modulus of z is equal to 1. If we assume that the modulus of z is equal to 1, then we can get rid of the r and we can just write that z is equal to cosine theta plus I sine theta. And so this is true for any z on what's called the unit circle on the Argand diagram. If we take the points like this, where this is the point 1, this is minus 1, this is I, and this is minus I, every point on that unit circle, every point with modulus 1 can be written in this form without the r, which is quite nice. And that's what we're going to be using right now to help us with these trigonometric identities. Because it leads us to another interesting note, that if I take this z and turn it to the power of n, well, that's equal to cosine theta plus I sine theta to the power of n, which by de Moivre's theorem is equal to cosine n theta plus I sine n theta. And that's going to be really, really helpful because there is another option as well. What if I put z to the power of negative n? Well, we're going to get cosine theta plus I sine theta to the power of negative n. And that's going to be equal to cosine of negative n theta plus I sine multiplied by negative n theta, again by de Moivre's theorem. But there is an interesting thing to note about sine and cosine. If you think about the graph of cosine, it is perfectly symmetrical around the y-axis. So if I do a reflection in the y-axis, i.e. multiply it by a negative 1, it stays the same. And so it's for cosine, it's true that cosine of n theta is identical to cosine of negative n theta. Sine, on the other hand, is somewhat different. For sine, it is anti-symmetric, as you might say. It's got rotational symmetry about it. But the key thing is that any value I take over here, so if I go to theta along here, the value I get there is exactly the same as if I go to negative theta, it gets the negative value. So what we get for sine is a very similar statement, but we get minus sine of n theta is identical to sine of minus n theta. And that there gives us, you notice that the negative sort of comes out the front. And that gives us a power to manipulate this expression up here. Because what it tells us is that z to the negative n is going to be equal to cosine, the negative can just disappear, cosine n theta, and for the sine it comes out the front, so minus I sine n theta. Now taking these two together, let's write them out again, we get z to the n is equal to cosine n theta plus I sine n theta. Z to the minus n is equal to cosine n theta, almost exactly the same, minus I sine n theta, almost the same. And now we can use a trick that is often probably used in simultaneous equations and add them together. And what I will get is that z to the power of n plus z to the minus n is equal to, well, I get two lots of cosine n theta when I add those together. But if I add I sine theta and then add the negative I sine theta, that cancels out to 0. We get nothing. So in fact, we get that z to the n plus z to the minus n is equal to 2 cosine of n theta. And we've eliminated the signs from it entirely. We've got a way of writing this complex number without the signs at all. And similarly, if I subtract, well, the cosines are going to cancel out, get 0 there, and I get positive sign subtract negative sign. If I subtract negative, I'm adding it on, so I get plus 2I sine of n theta. And these two are the two formulae that we need. We can get rid of that 0. Z to the n plus z to the minus n is 2 cosine n theta, and z to the n minus z to the minus n is equal to 2I sine n theta. And very often we write it without the negative on the power. So z to the n plus 1 over z to the n is equal to 2 cosine of n theta, and z to the n minus z to the minus 1 over z to the n is equal to 2I sine of n theta. Okay, so this is what we're going to use. And we've got a particular case. If you say n equals 1, then we have just that z plus 1 over z is equal to 2 cosine theta, and z plus 1 over z is equal to 2I, oh, not plus there, minus 1 over z is 2I sine theta. And this is what we're going to use to prove these formulae in a different direction. So in this case, what I want to do is, rather than before we were finding formulas for, say, cosine of 3 theta in terms of powers of cosine, we're going to do the other way around, and I want to find a formula for cosine to the power of 3 theta in terms of like a cosine 3 theta plus b cosine 2 theta, etc. Okay, now how are we going to do that? Well, we're going to use exactly this here. If I want cosine of 3 to the power of 3 theta, then what I'm going to consider is 2 cosine theta to the power of 3, which I know is going to be z plus 1 over z to the power of 3. And let's put these z's in different colours for now. And so that's going to give us, well, expanding this, I get 8 cosine cubed theta. So that's quite nice. I've already got the cosine cubed. And on the right hand side, we're going to use the binomial theorem, and we're going to get z cubed plus 3, that's our binomial coefficient, z squared multiplied by 1 over z to the power of 1, plus 3, binomial coefficient again, z, 1 over z squared plus 1 over z cubed. And we can simplify this, and we get z cubed plus 3 lots of just z, z squared divided by z is just z, plus 3 lots of z multiplied by 1 over z squared, we're going to just end up with 1 over z, and then this is going to be 1 over z cubed. And now you might be thinking, well, how does this help me? This doesn't look anything like cosine or sine. but actually we can group them together in exactly the groupings we saw earlier using this principle up here, that z to the n plus 1 over z to the n is equal to 2 cosine n theta. So we want to connect things with the same power, but where one is the reciprocal of the other. So we're going to say that this is equal to z cubed plus 1 over z cubed. Notice how they have the same power, but one's the reciprocal, plus, and let's factor out this 3 lots of z plus 1 over z. And so this bit and this bit came here, and this bit went there. And we're just factorizing out, rearranging like that. We wrote earlier that z to the n plus 1 over z to the n was equal to 2 cosine n theta. So I can substitute that in. In the first one, for the blue one, our n is 3, so we get 2 cosine 3 theta. And for the green one, we get 3 lots of just 2 cosine theta, because our n is 1 there. This is obviously to the power of 1, power of 1. And so we get 8 cosine cubed theta is equal to 2 cosine 3 theta plus 3 lots of 2 cosine theta. And then all we need to do is simplify and divide by 8. So we get cosine 3 theta divided by 8. 2 divided by 8 is a quarter. 1 quarter of cosine 3 theta plus 3 times 2 is 6. 6 divided by 8 is 3 quarters plus 3 quarters of cosine theta. And there you go. That's all there is to it. That's how you can write something like this down here, cosine to the power of 3 theta, in terms of triple angles, single angles, double angles, etc. And you can do it for any of them. Be careful if you're going to do sine, remember it's 2i sine of theta to the power of 4 or whatever you're dealing with. Do not forget that I. That's very, very important and will mess you up if you get it wrong. And there's one more thing this allows us to do. Because let's say I was asked to integrate cosine cubed of theta. Well, I don't know how to integrate cosine cubed, but I can integrate 1 quarter of cosine 3 theta plus 3 quarters of cosine theta. That's actually pretty easy. I wrote dx, I should be writing d theta there. That's pretty easy because 1 quarter of cosine 3 theta, well, that's just going to be sine of 3 theta. And then I need to remember to bring the 3 out, but the 3, it's integration, it gets divided, so it's 1/12 of sine 3 theta plus 3 quarters, and there's nothing inside here, so it's just sine theta plus c. And that's all there is to it. There we go. We can now integrate cosine of 3 theta, cosine cubed of theta, really easily just by writing it in that form. Okay, thank you very much for watching, and I will see you in the next video.